Hello and welcome to our lecture today on model assessment and selection. So this lecture is in many ways similar both in style and content to our lecture on the bias variance dichotomy. It's similar in style in that we're not going to be teaching you a new technique, but we're teaching you a concept in machine learning that's really important. And so like the bias variance dichotomy, it is really applicable to almost every technique that you could be using in machine learning. And I should not just say every technique in machine learning, more narrowly in every technique in supervised learning, right? So your regressions, your neural networks, your carts, your decision trees, your SVMs, so whatever techniques you're learning right now and whatever you have learned, this is a very, very important concept. It's also very similar in content because in the bias variance dichotomy lecture, you really learnt about how it's really important to understand that you can have highly simplistic models which would have a high degree of bias and low variance and therefore not really good. And at the same time, you can have highly complex models which tend to overfit the data and therefore have a lot of variance but very low bias. And therefore, we introduce a problem there, saying that, well, it's not a good idea to go to either extreme. In today's lecture, we will be coming up with solutions for that problem. And not just that problem, for many other related problems, but somewhere the solution is in looking more carefully towards how do you assess a particular model, and therefore how do you go about selecting between multiple models. Okay, so jumping into the subject, in terms of when you have data and you're trying to use the data towards models, right? There's one part which is actually using the data to train the model. Okay, there's another part which is you could use some of the data to not just train the model, but to choose between models or to fine-tune the model. So using the data to train the model is model training. Model selection, the word selection is used kind of loosely here. It could mean selecting between multiple models, or it could mean, meaning you could use that to select between completely different models. Or at the same time, you could use that, you can fix the model, and it could just be like parameters that define the model, and you could go about figuring out what value to set it to by using data in the model selection. And finally, you have the concept of model assessment, which is once you've fixed everything up, right? If you wanted to get an idea of how good this model is, so that you know that when you take this model to the field, this is the performance you'll expect, that has to do with model assessment. And corresponding to these three goals or objectives, you could break up your data. And this is something that you might not always have the luxury to do, but you can if you have a data-rich situation where you have enough data. Then you could potentially break up the data into training, validation, and test, where the training goes towards model training, the validation goes towards model selection and fine-tuning, and the test goes towards model assessment. And there's no formula exactly as to what this breakup should be or what is enough data. That's a hard question to answer. It varies from case to case. But at the surface, typically if you have enough data, you tend to break it up as either 50%, 25%, 25%, and finally 25% out here. 50, 25, 25. But you could also have 60, 20, 20. And again, even for this, you can't say one is right, one is wrong, or something is perfectly right or wrong. I'm just giving you some values that are typically seen. You can also see in the picture that the representation I have below, that sometimes you might want to do training and validation together, and we will talk about that more specifically. But this sometimes comes up when you don't have as much data. where you don't have the luxury of just taking 25% and calling it validation. So somewhere, you just use the same data to perform training and validation, and how you'll do that is something that we're going to talk about in good detail in this lecture. But you still try to keep some percentage for model assessment. The final say on how good the model will be if you take it out to the field. If the model were to completely look at new data and try to predict how good will it work. Okay, so what we're going to do next is we're going to take each of these phases and talk in detail about what really we can do for each of these objectives. The first phase, which is model training, is one where you take the data and you train, right? What we mean by training out here is really that you fixed everything. You fixed all your steps. You've chosen a particular model, and you've chosen all the parameters associated with this model. So at this phase, you're not doing any model selection. In phase 1, you're not doing any model selection, no selection. You've also not trying to decide on what values that some of the modeling parameters should be. What I mean by that is, let's say you're doing a ridge regression. In ridge regression, you have a complexity parameter. If you go back to our lecture on ridge regression, you are doing this optimization where you're doing the ordinary. It looks like the ordinary least squares, but you have another term, right? This is the term associated with regularization, where you penalize really large coefficients. So for that, you need to set a value. You need to set a particular lambda. You've already decided that in this phase, right? When you go in for data for training, you fixed the model and you fixed all the parameters associated with the model. If you're, for instance, doing a neural network training, you're not using this data to decide how many intermediate nodes should be there. That's not what's happening. Once you've finalized on the exact model and its details, you are just using this data to figure out what the model should be. Meaning, take the case of a linear regression, right? You fixed everything. You fixed what the input variables are. You fixed what data you're going to process. With respect to a simple linear regression or a multiple regression, there are no other parameters to fine-tune. So you just plug in the data and you get the betas, right? So here you might just be getting the betas. So that you've created the model. You're essentially creating the model in this phase. If you're doing decision trees, then let's say you need to have fixed on the algorithm for the decision trees. You need to have fixed what the input variables are. You need to have fixed other parameters that you could probably play around with in decision trees. And we're going to talk about those parameters soon. But once everything is fixed, you just plug in the data, and out you get is a tree structure. Tree structure. Or network in the case of a neural network. So this is essentially the last leg. Once you've fixed everything, you're not doing any model assessment, you're not doing any model selection. You've already selected your model, you've already set the parameters for your model. You're just plugging the data into this finalized version and getting the actual model out of it. So that's what you're doing in this data for training. What happens in the validation phase? In the validation phase, you're essentially using this data. So this is separate data, right? You use some data for training. Now think about this. You're using separate data, and you're using this data to make some decisions. You could be using this data to select between multiple methods, right? So you might say, hey, I have this data. I could do a linear regression on it. I could do a regression tree on it, or a random forest or something. I could do a neural network. How do I know which to do? Why not do all of them and see which one does better, right? And how do you see which one does better? In the validation phase, what you'll do is you'll use the same training data. That is, you'll use the same training data that we discussed in 1, right? And you'll fit these 3 completely different approaches. You'll create the betas for the regression, you'll create a tree for the regression tree, you'll create a network for the neural network. Now you go apply these 3, right? You go apply these 3 to the validation data. What I mean by that is that you go take the input data in the validation and apply these three methods, and you get some predicted outputs. Right? Each of these methods are going to give you some completely different, might not be completely different, but they're going to give you different outputs, different predictions. Compare these predictions to the actual output that you have in the validation data. Right? When we say data, whether it's for training, validation, or test, it means you have input-output pairs. Right? So if you have 5 input variables, you'll have values of each of those 5 input variables. One data point is nothing but the vector of all values of the 5 input variables and the one output variable, so whatever value that is. So in some sense, when you have these input-output pairs, what you can do in the validation phase is you would have created the models from the training phase, and what you're interested is in comparing multiple different models. So you might have completely different methods, and then you apply the input of the validation phase to get predictions from these methods, and compare these predictions to the actual output and see how well they did. And you can do that by both in a regression context or a classification context. Meaning that if you predicted 13 and it's 13.5, I can say, you missed by 0.5. If you predicted that it's going to be a class, like I'm predicting that there's a 70% chance it's male and then it winds up being female, you can say you can use a different kind of a metric to measure that performance, like misclassification index or entropy or something. But essentially, the idea in the validation phase is to make some decisions. We spoke about how you can use that to choose between methods, but more often, right, what we see is that it's used extensively to fine-tune parameters for a given algorithm. So let's say I go about and I've decided, right, at this stage. So we've already talked about, let's call this A, B, and C. So we've already talked about 2A. Okay, in 2B, what I'm really talking about here is, let's say I've decided that I'm going to use a decision tree. Okay, so I'm going to use the CART algorithm. Now the CART algorithm might have a lot of parameters that I need to set. One potential parameter could be the minimum number of leaves in the terminal nodes. What that means is the minimum number of data points in a terminal node of a tree. Right? So in a CART algorithm, you can keep on splitting the tree into branches and branches till the terminal nodes just have one data point. The idea is, where do you stop? And one way of choosing where to stop is to have a limit. You put in a limit saying, don't create new branches if they're going to result in the final nodes having less than, let's say, 5,000 data points, or we call them 5,000 leaves. But what should that be? Should that be 5,000? Should that be 500? Should that be 50,000? Right? What you can do is you can run all of them. You can create 3 completely different trees, one with each version, and again validate that. Use the validation data set to see which does better. Right? And for pretty much any method, any complex enough method, you'll find that the method itself will have some parameters that you need to finalize. So in the case, I guess you guys have finished, you might not have started neural networks yet, but you must have finished. So we finished ridge regression, right? So again, let's think about ridge regression. In ridge regression, we know that what ridge regression does is it does this process of regularization by introducing a new parameter called lambda. Right? Lambda is what forces lambda is kind of like the way in which penalty is applied towards that optimization problem and constrains the size of the betas. So if you have a very high lambda, that's like a very harsh penalty towards large sized betas or coefficients in that linear equation. So ridge regression goes ahead and applies this penalty. Now if the lambda, which is this parameter, is very low, it's close to 0, then there is no penalty. The ridge regression becomes like the ordinary least squares regression. right? It's actually identical if that lambda is exactly set to 0. But then the question comes about, what should I set lambda to? I understand the concept. I understand the concept that I might want to apply some amount of penalty to really large betas, and that was what we discussed in the course on regularization, saying, I can, if I have multicollinearity in my data, I might have two betas that are of two opposing magnitudes that are becoming really large, and so on and so forth, right? But what should I set the lambda to be in the ridge regression? In the process of ridge regression, I need to set the parameter lambda to some value, and what do I set it to? Is there a right answer to it? The answer is, you might not know that a priori as to what to set lambda to, but you can use this validation phase, right? You can set lambda to 0.25, set lambda to 0.5, set lambda to 0.75, and create three different regression equations, three different predictors. Now, take the input data from the validation set and apply that on all three predictors. All these three predictors will come up with some predictions, three different sets of predictions of the validation data. Compare the predictions of each of these predictors. Compare these three sets of predictions to the actual output data of the validation data set. And you can then compare these three and say, oh, it looks like when I set penalty parameter lambda in ridge regression to 0.5, I do better than when I set that parameter to 0.25. Okay, so again, just you can go to the bank. I know you finished a subset of techniques and you're still going to learn, for instance, neural networks and some other methods. But what you should commit to memory in some sense is that almost any machine learning technique that you adopt, you'll have to choose some parameters, and this validation can help you choose the parameters. Oh, another example I can think of is, for instance, the k-nearest neighbors. What should your value of k be? Right? Am I supposed to be looking at 5 nearest neighbors, 6 nearest neighbors, 10 nearest neighbors, 1 nearest neighbor? What should, in a k-nearest neighbor algorithm that we discussed in our class where we compared regression to k-nearest neighbors, what should the value of k be? And you can use this validation to figure that out. Okay. The last use case in some sense of the validation phase is one that can also be used to choose the correct number of input variables and to also say which ones those input variables should be. So it's choosing the correct number and also choosing those which. So I can say I need 5 input variables and not 6, but which 5 should they be? So in that sense, and this kind of really links up with best subsets regression, right? Where you're trying a whole combination of different inputs. Again, the idea could be that I could have a fixed model. I could say I'm going to use ridge regression, or I'm going to use regression, or I'm going to use trees with this parameter. But which inputs should I be using? Should I use all my input variables? Should I use input variable 4, 7, and 9? So that decision also sometimes, like we spoke earlier about regression, your R square will just keep on getting higher and higher as you keep on adding more inputs. That does not mean you're getting a better model, right? So choosing those inputs is, you can choose a model with inputs A, B, C, D. Another one where you use inputs D, E, F, G, and you can really compare the performance of these two different models on the validation data set. Now, there are some techniques already there that we have discussed which helps you choose what the input should be, and we've spoken about that using metrics that are more complex than R square, like for instance adjusted R square, which goes ahead and penalizes more complexity, and there are a whole bunch of blanket approaches to penalize more input. So we spoke about adjusted R square. There's something called the Kiki information criteria, AIC, and then there's the Bayesian information criteria. So there are a whole bunch of metrics that will just go in and say blanket, I'm going to penalize you for adding more input variables, but we don't need to do that. While that might be computationally convenient, and it is, you could, if you had the luxury of creating this validation data set, a simple thing that you could do is you can just try these different combinations of inputs for the chosen method of doing the training and so on, and apply them and see which approach does better. So you don't, so you could just ultimately wind up using prediction error instead of say something like adjusted R square. You can use a prediction error because you're not just blindly looking at how good the model fits the data that you trained the model on. You're now taking that data that the model has never seen when it trained, and you're using that to decide what your input variables should be, or how many input variables you should have. So the important thing is the validation itself, and this whole process of model selection is not just one thing. You could use validation really to choose between multiple methods. You can use that to fine-tune the parameters of the algorithm, and you can also kind of use that in some way to choose what your variables should be. Okay. Finally, you have the test phase. Now we're at number 3, right? The test phase. And we had 3, and now we're talking about 3, the test phase. The test phase, the purpose is different. It's not to fine-tune the model. It's not to help you come up with the best model. You could have come up with a good model. You could have come up with a horrible model. The test phase says, I don't care. My job, the job of the test phase is fairly simple. The job of the test phase is to give an accurate idea of what the performance of this algorithm is going to be, right? And you can turn around and say, why don't I just use something like my prediction error that I got in the validation phase? And the answer is you cannot, because you have hell, I mean, you can go even one step further and say, why can't I just look at the predicted the error, the residual sum of squares in some sense, the error that comes from the training, right? You cannot do that for the simple reason that you are explicitly fine-tuning the model, fine-tuning the coefficients, fine-tuning the parameters, irrespective. And this, I'm loosely using these terms because it applies to any approach you take, whether it's decision trees, whether it's discriminant analysis, whether it's support vector machines, whether it's neural networks, whatever approach you take. There's a whole bunch of optimization going on in these approaches, right? You're sitting there and you're trying to make this model make sense out of this data. That process itself is going to make you do very good on this data. Now, to get a true picture of how well you'll do when you see new data, you don't want data that was used to make this method good in the first place. Right? You use some data in the training data to figure out the coefficients. You use some data in the training data to construct the actual tree or the actual network. You use some data in the validation data set to fine-tune what your parameters should be. Why? So that you do a good job of fitting. Now, you don't want to use the same data to tell me how good I will perform when tomorrow someone comes to me and says, here is this input data, can you come up with a prediction for me? Right? To do that, you want to really look at data that has never been looked at. Essentially, this is you should think of this as data that's been kept in the vault and never looked at, and you're bringing it out in the end after all the modeling has been finished. You've used the training data to construct the trees. You've used the validation data to fine-tune it. You now have end product. The end product in a regression could be a set of coefficients like the betas. The end product in a tree could be the tree structure. Whatever it is, right? You basically have a finalized end product, and you want to now see how good the end product works. Now pull out this data. Pull out this data, provide the input data from the test data set, ask the model to make predictions, compare it to the actual output, and you're just going to report that. You're not going to use this data to make any more decisions in terms of which method to use, or you're not going to use this data to fine-tune anything about your model. Okay? Because if you're doing that, you're using the data to make the model better, but you're not giving any longer an accurate impression of how successful you would be if you were to completely see this data afresh and you were to make predictions. You're not giving an assessment of the model. Okay, so in order to give an assessment of the model, pull out this data that has never been seen by the model in the end, and the only purpose of this data is to see how good the model is, not to construct the model or not to fine-tune the model. Okay, so that's the test phase. Now we're going to talk about in the last part an approach called cross-validation, and it really ties to this case that I showed you in the first slide, where the training and validation are kind of put together. This is an approach that really kicks in when you feel like you don't have enough that much data for a separate validation set, and you want to kind of squeeze more out of it. Okay, so a simple approach there is to just have the training and validation set as one large data set, and you can break it up into n chunks. So out here I've broken it up into 5 chunks. Going between 5 to 10 is typical, and the approach is called actually k-fold cross-validation. So it's k-fold where you have to choose a particular k. Okay, and here I've chosen 5, and so basically broken the data set into 5 chunks. Obviously, very important, guys, is that this breakup is random. So if you're given the data in some order, you don't want to very conveniently just break it up into 5 chunks, and because there might be some kind of implicit order. Maybe the data was, for instance, chronologically ordered, right? You don't want to create training data set 1 of the early chronology data. So you kind of want to shuffle the data up and then break it up into 5 bins. And the idea is to use any 4 bins to train, 4 to train, and 1 to validate. Oh, so you might sit there and say, hey, this just sounds like you're breaking up the training and validation at a later stage than at an earlier stage. But the answer is no. There's one more step. Once you do that, shuffle them around, meaning now in this particular graph I've shown you, let's call them 1, 2, 3, 4 and 5, right? In this graph you're using 1, 2, 3 and 5 to train, and you're validating. So this is train, and you're validating with 4. Now permute. Okay, in the next step, do 1, 2, 3, 4 and validate on 5. Next step, permute 2, 3, 4, 5 and validate on 1. And so like that you'll keep going till you've done all the 5 combinations where you would have validated on separate. And you take the cumulative validation results. So you'll take the cumulative validation results to see how well to make decisions in terms of validation. And so this is called k-fold cross-validation. So one question that comes up fairly frequently is what should the value of k be in a k-fold cross-validation? Given you a tentative idea that it's typically somewhere between 5 and 10, but again that's not something that's cast in stone, and it's more important that you understand what it means to choose a high value of k versus a low value of k. In the simplest sense, a high value of k in a k-fold cross-validation leads to a model leads to an assessment, I should say, which is of very low bias but of high variance. Okay, and a very low k, so a k of like 2 or 3 or so, essentially could have low variance but a higher bias. And one extension of, for instance, the cross-validation where you have a very high k, right, where you're likely to have an unbiased assessment, but an assessment with lots of variance, is the case of the leave one out cross-validation. The idea here is that if you have n data points, I'm going to use n minus 1 data points to do the training, and I'm going to validate on that one data point that I left out. And what I'll do is I'll keep, just like in k-fold cross-validation, how you change the training sets and the validation sets, how you shuffle them, how you permutate them, the same way you're going to leave one data point out for validation, train on the others, and then predict on this, and then keep doing that iteratively. So obviously with there, when if it's essentially like k is equal to n, then the cross validation is almost completely unbiased, but can have high variance because the n training sets are so similar to one another, right? And an approach like that is also computationally fairly cumbersome. But if you have that approach, then the leave one out cross validation is also something that you might consider. So I hope that gives you an idea of cross validation and more broadly the use of the idea behind validation as a means of model selection, and this whole thing of breaking up training for creating models, validation for assessing and kind of selecting models, and test for pure assessment with no further selection and decision making. Thank you.